Everyone, and welcome back. So we're in Chapter 8 now, and Chapter 8 means bending. So today you're going to understand how to determine normal stresses and flexural strains due to applied transverse load, and be able to calculate the centroidal moment of inertia given a cross-section. So let's jump right into this. Now first off, why do you care? Well, have any of you ever jumped off a diving board? In all honesty, I don't think I actually ever have. But when stepping on a diving board, you do expect it to bend. It's not going to be this perfectly stiff thing. You're going to jump on the end and nothing happen. No, it's going to bend a little bit. It's going to flex. But how much will it bend? Will a 30-pound child be able to get on there and not have it bend all the way in half and drop them in the water? Hopefully not. Will a 200-pound man be able to do that? We don't know. So what's going to control how much it moves? How much it deflects? How much it bends? Well, that's something we're going to start learning about today. So first off, let's get some terminology out of the way. So beams are one of the most common type of structural members. And they come in a wide variety of shapes and sizes. But they usually share a few important properties. They're all long, compared with their cross-section at least. They're typically straight, prismatic, which means they have that constant polar moment inertia, and they can support transverse loads. Now, those transverse loads are going to cause that beam to bend and flex. Transverse being pushing down, not against. So not that one, just one pushing down against it. Okay, so here you go. You can see some transverse load applied to a beam, and then they're going to cause deflection. So it's going to have this curved shape. Now we haven't gotten to the point yet where we can determine what that curved shape is going to be, but we'll get there. But for now, what you should hopefully be able to guess is that if we're looking at the top of this, there's going to be a stress induced there, as well as on the bottom. One's going to be tension, the other compression. One's going to be having a positive strain, the other a negative strain. One gets short, the other one gets longer. That's all because of how it is curving along this deflection curve, or elastic curve, however you want to call it. Now, initially, we're only going to consider beams that have a plane of longitudinal symmetry. Okay? That simply means that if I divide it in half, I see the same thing on both sides. Now, we have to come up with a coordinate system, which is usually going to be at the base of our beam. And that x-axis is usually designated as the longitudinal axis. When you say longitudinal, think long. It should help you there. Now, the bending is going to occur in the xy plane, and that's why it's called the plane of bending. So we either go up or down, and just hopefully we won't get any in the xz plane, because that is not good. That's the weak axis for most columns. Most beams, cause it to fail. Our bending is said to occur about the z-axis, because if you look at this, if this is a moment, it's curving around what axis? The z-axis. Okay. Now, various times today, I'm probably going to talk about longitudinal fibers, and you'll definitely see this in your textbook. Now, that came because, originally we were making beams out of wood, and they literally had fibers. They were fibrous material. Metals don't have fibers. They technically have grains, which can be very long and thin, kind of like fibers. But we're going to still use that term today. Just think of it as a bunch of flat segments that are all kind of glued together to make that metal beam or whatever beam. So because of this, if we look at the longitudinal fiber on the top, we can see that it's going to be in compression because it's gotten shorter. So that's a negative strain. It's going to cause us compressive stress. But on the bottom, however, it's in tension because it's gotten longer because of how we bent it. So these different fibers are going to be experiencing different stresses and different strains. Now, another important term here is going to be called pure bending. Pure bending. Pure bending is when we have a constant moment right here. The only time we have a constant moment is when our shear force is zero. That's the internal shear force. So you'll see it in these fairly symmetric cases. I've got two loads in the end and then two loads in the middle, and then that cancels out my shear force for the middle. Right there. That would be the section that would be in pure bending. It's got that constant shear force, which is equal to 0, and therefore a constant moment. It has to be constant and equal to 0. Don't forget that. And you can still assume pure bending as long as the beam is slender, even if it's not perfectly got a constant moment. So it's one of those times when like it's close enough that it doesn't really matter that it's not quite right, but we'll be correcting things as we go along. Okay, so that's where we're going to end it today. We've learned about beams, we've learned that they're important, and we've seen that these longitudinal fibers have different stresses being applied to them. We've also learned how we define when a beam is in pure bending. And so next time we're actually going to get into a lot of equations and talk about how we can calculate strains as we move our way through understanding how these beams work. So thank you for listening, and I'll see you all next time. Bye-bye.